So we call the operator pi, and we defined it like this here. So it changes the position eigenstates from x to minus x, and so this operator is unitary with eigenvalues plus and minus 1. So if psi is a parity eigenstate, then it has a well-defined parity, so it's even or odd, just like we have here. Then we also worked out the commutation relations between pi and x and pi and the momentum operator p. So they commute, but it commutes with the angular momentum operator. So I think we are here this time. So the commutativity of the parity operator and the angular momentum operator means then we can choose simultaneous eigenvectors of j and pi. So if Lm is an eigenvector of j or L in this case, then this is also an eigenvector of the parity operator. So we can see this by considering the spherical harmonics. So we know from spherical harmonics that if we reverse the direction, then that is equal to minus 1 L times M, and like this, yes. And this is just n pi and M. So then that is equal to minus 1 L M, like that. So then we see that pi L M is equal to minus L times state Lm. So the angular momentum state has a well-defined parity given by minus 1 to the power of L. So for example, if you have an s orbital, so that would be L equal to 0, then it is symmetric under inversion. But if you have p states, p orbitals, so that corresponds to L equal to 1, then you know that it has is not invariant under parity. So x becomes minus x, for example. So that's the parity property. Now there is a theorem related to symmetry under inversion. So we have a Hamiltonian which commutes with the parity operator. Then we can show, it's not difficult to show, that it's a non-degenerate eigen energy eigenket. is also parity. Now, of course, if pi commutes with h, then we can always construct simultaneous eigengets of both h and pi. But specifically, if the state is non-degenerate, then it must be a parity eigenget. So I can show this quite simply by looking at the state n. So let's say that n is an eigenket h, so that is equal to n, like that. So if we look at this state here, and we say that uh, we have, because of this commutativity, it implies that this state is also an eigenstate of h with the same eigenvalue. Okay, so that's just because of the commutativity. If the state is non-degenerate, then it implies that I n must be proportional to n. So it has to be just some c, constant c times n, some phase factor. So if we apply this again twice, then we get c squared. But we know that pi squared is equal to 1 from the previous result. So then this implies that c must be equal to plus minus 1. So we go back here, then we see that the state n must be an eigenstate of the parity. So that's simple proof. So the fact that the state is non-degenerate is important, because if the state is degenerate, so if you have several states which are degenerate, then it is not necessarily that the states have definite parity. Yeah. So a simple example of this is I think I give in the note here. It's a plane wave. If you take a plane wave, it will be like k dot, or let's say in one dimension, it will be just I kx, so a free particle. But e to the minus ikx is also an eigenstate of the free particle, same eigenvalue. So these two are degenerate. So that is, but both these states do not have well-defined parity, because if I change x to kx, then this will become e to the minus ikx, and this one goes to e to the minus plus ikx. So they don't have the parity. Yeah. But of course, we can form linear combinations of these two that gives us the parity, gives the correct parity. So if we form e to the ikx plus e minus kx, so that gives us then the cosine. So just 1/2 here, of course. That will be a cosine kx, which is even. And if I take the minus, it will give me a sine kx, which is odd. So because of the commutativity of the parity with respect to Hamiltonian, then we can always find always construct simultaneous eigenkets with the proper symmetry. But they don't have to have this symmetry if the states are degenerate. But if the state is non-degenerate, then it must have a well-defined parity. So let's consider an example of oh, I think I should yeah, okay. I want to consider an example of symmetry breaking. So, spontaneous symmetry breaking. Or just broken symmetry. Broken symmetry solutions. A simple example of this is given in the book. So let me try to first draw the picture here. So this is from figure 4.3. So we have a double well separated by some barrier like this. So then if we look at the two lowest solutions, energy solution, then we have the symmetric solution. This will be like, I'm not so good at drawing here. Something like this. Oh, should be like this, more like that. And we also have the antisymmetric solution. Yes, so it's a one-dimensional potential. The states are non-degenerate, so then they have well-defined parity. So this is an example. Yeah. These states are non-degenerate, so they have well-defined parity. So this one is symmetric. Symmetric, so we call it S, natural S. And this one is antisymmetric. Call it A. So then we also note that the antisymmetric solution must have a higher energy because it has a node. So then the energy of the antisymmetric solution is higher than the symmetric one. So let's have a look at the linear combination of these two. So call it R. We call linear combination of the symmetric and antisymmetric solution. And left, see, is it correct here? Yes. Minus A like that. And you can see that why this is called right and left. I mean, if you sum the symmetric and antisymmetric solution, then most of the wave functions will be concentrated on the right well, because this part will kind of cancel that part here. And the same here, yes. So that one will be concentrated on the left well. So that's why we call it R and L. So now we had a look at how this states evolve in time. So let's say that we start time t equal to 0. We assume that the particle is mostly located on the right hand side. say that this we start with states R. So this is not an eigenstate. Yes, this is not an eigenstate. It's not an eigenstate. Because it's a linear combination of the symmetric and antisymmetric solutions, and they have different energies, so this cannot be an eigenstate. So let's have a look now at the time evolution of the state. Then we use the word time evolution operator. So this is an example that the time evolution operator is rather useful because we just multiply this or apply the time evolution operator on the state. That gives you the time development of the state. So if we do this and we use this R here, so both of these are eigenstate of H, so that's easy to calculate. So that gives me then to the minus ES T H bar S plus to the minus I EAT H bar A, like that. Now if we rewrite this again in terms of the right and left states, so of course I can also write this state as plus side 1. The antisymmetric would be 1 upon square root of 2 or minus L, like this. So if I use it here, then the little algebra gives me this result here. So I skip that step. It's quite straightforward. Yeah. Then it becomes a cosine omega t plus I sine omega t L. So if we look at the probability of finding this state on the R and on the right and the left states, then we see that they kind of oscillate. Yes. So let me calculate the probability of finding this state on the R. So that would be then cosine squared omega t, whereas the probability of finding it on the left state is then must be just sine squared because they have to add up to 1. Those are the only two states. So we see then if we plot this, then we will get something like cosine like this and the sine like this. So this will be the cosine squared, and this is the sine squared. So it oscillates, the system will oscillate. So at one point, so this is 1 here. It's a function of time here. So at one time, it will be completely on the left, and At another time will be on the right, and it will oscillate between the two according to this cosine and sine. Yeah. So the oscillation frequency omega is just given by so h bar omega is just 1/2 of the difference between the antisymmetric and symmetric energies. So what's interesting is when we consider the case where the barrier becomes larger and larger. So we increase the barrier, and we have a situation like this. So this will become very, very large here. So let's say this is infinite. Then, if we just look at the solution, and there will be a symmetric solution like this, and we have the anti-symmetric solution like that. So we now do not have any weight in the barrier region because it's infinite, so the particle cannot penetrate inside the barrier. So the wave functions are completely confined either on the left or on the right. Well, yes, can only have weight. Yeah. So if you look at these two solutions, then they are degenerate because they are exactly the same wave functions, basically, except that one has a minus here, and one is positive here. This is minus, but otherwise they are the same wave functions, so they have same energies. So in this case, it becomes degenerate. And the right and the left solutions are also degenerate. Yes, because these R and the L are just linear combinations of the symmetric and antisymmetric solutions. However, these two solutions do not have the symmetry of the Hamiltonian. Because obviously, if we look at, let's say, the R state, then the wave function is completely localized on the right. So this will be like having a state like this. It's completely localized here, whereas the left one will be completely localized on the left, like that. So they don't have the symmetry of the Hamiltonian. And that is okay because they are degenerate. So there is no requirement that the states must have well-defined parity. Whereas for the case when the barrier is finite, then we know that the states must have well-defined parity. So the interesting thing is that since the barrier is very large or infinite, you can think of it as being infinite, then if we have a particle, let's say localized on the right, say here, then it will remain there. It will not tunnel to the left. Well, and the same if we put the particle on the left. So there is this sort of a broken symmetry solution corresponding to this right and left solutions. So the ground state then do not need to have a well-defined parity. So one example, one famous example of this is also given in the book, is the molecule, the ammonia molecule, NH3. So this is a molecule with 3 hydrogen atom, like this, forming a triangle. And a nitrogen atom somewhere here. So this forms like a tetrahedral, I think. So yeah, something like that. So if you look at this, the structure of this molecule, then there should be another form, another structure in which the hydrogen molecules lies down here. Let's see here, like this. Yes. So there are two configurations where the nitrogen atom can be above the plane of the hydrogen or below. So these two configurations should have the same energy. So this is an example of the simple model that we just considered of this double well. So this is a bit like the right, or you can call it the left also. And this will be then the left state. So there is a very large energy barrier in going from this configuration to that configuration. So if you try to push the nitrogen atom through this hydrogen plane, then obviously you will need to supply a lot of energy. You have to do a lot of work to go from this configuration to that configuration. So because of this energy barrier, once the system is in this state, it will remain there. It will not go over to this state, or at least it will take a very long time to go from this state to that state because of this energy barrier. So the double well case that we consider is a kind of model of this ammonia molecule. So the one configuration corresponds to the right state and the other one corresponds to the left. And there's an energy barrier in this too. So I can give you another example of this. Another interesting example of this is magnetism. So a famous Hamiltonian, which is very widely used to study magnetism in real systems, is the Heisenberg Hamiltonian. Heisenberg spin Hamiltonian, or just Heisenberg Hamiltonian. So this Hamiltonian has a rather simple form with minus j here. So j here has nothing to do with angular momentum. It's j is just some number. It's called the exchange constant. Then sum over ij. So I will explain what this means here in a moment. Sorry, this is not j, but I want to write s, spin. It's j like this. So these are vector operators. Yes, the spin operators. Si dot sj. So let me put the vector here to make sure that they're just vectors. So this symbol here means that we only have nearest neighbor interaction. Nearest neighbor. Maybe you cannot see this. Nearest neighbor interaction. So you imagine you have, let's say, just a one-dimensional lattice. So you have sides here like this. So you have spin. So let's say spin half. Let's say on each side like this. You have spin here. You have spin here. You have another spin here, and so on. So this ij labels the sides, and we have an interaction between this with the strengths j. Okay. So what's the solution of this Hamiltonian? Um, we can rewrite this dot product between the Si and Sj to be equal to, so let me write the full thing, so H minus J sum over J, like that. So that is then equal to, so we can rewrite this as put here I put a Z here, maybe J plus 1/2 of Si plus Sj minus, that's the ladder operator, plus like this. Yes, we can rewrite it like that. Then we realize immediately that the ground state solution to this Hamiltonian is quite simple. So we have a ground state, which looks like this then. So all the spins line up on each side in a certain direction. So what's interesting about this Hamiltonian is that if we look at the form of the Hamiltonian, it is a dot product between two spin vectors, psi since j. So then it should be rotationally invariant. So if I make a rotation, it should not affect this Hamiltonian because it is a dot product. Yes. So it is invariant under rotation. It is invariant under rotation. However, if you look at the solution here, clearly the solution is not invariant under rotation. Because if I make, for example, a 180 rotation, then I will get another ground state, which looks like this. So it is also an equally valid ground state solution. So this is like the analog of the right and the left solution. And indeed, there is a large energy barrier in going from this state to this state. Because if I try to flip the spins one by one on each side, that will cost me a lot of energy. So in nature, then the system kind of locked into a particular state. And it will take a tremendously long time to fluctuate between this state and this state here. So in reality, we just have one particular configuration, like here. So we have ferromagnetic systems. So if you think about iron, a crystal iron, it's a magnetic material. So the iron atom has a well-defined total spins. They're all pointing in the same direction. So these are that correspond to this kind of ground state. Yes, each side uh, has spin in the same direction. But also the Hamiltonian of the iron crystal is invariant under rotation. So the Hamiltonian actually says nothing about spin. If you write down the Hamiltonian of the um, crystal, there is no spin dependence. It's all just Coulomb interactions. So this is another example of broken symmetry. So this is broken symmetry. So the solution does not have the symmetry of the Hamiltonian, and that is all right because uh, this ground states now become degenerate. So there are lots of things like this in nature. There are many examples of this. So let's go back to the parity here before we go to time reverse. So there is another theorem concerning parity, and this is called the parity selection rule. So this is an example of the use of symmetry to calculate matrix elements. So by using the symmetry, we can tell whether this matrix element is 0 or not. So the theorem then says that if I have that's what I'm doing here. Two states, alpha and beta, and they have the same parity, then the matrix element of the position operator x here is 0 if they have the same parity. We can show this. Yeah, I think we have it in the notes also. So let's do it. And then I can introduce the parity operator. That doesn't do anything because it's just one. It's unitary. So then we have so since alpha and beta are eigenstates of the parity operator and they have same parity, then it has the same eigenvalue. And the eigenvalues can only be plus or minus 1. So if it is plus 1, then I can just replace this with alpha like that. Like that. And if it is minus 1, it's also okay because minus 1 times minus 1 is also plus 1. So then we have this. But this is minus x. So then this cannot be true unless the matrix elements is 0. So that proves the theorem. So if we have Hamiltonian with a non-degenerate eigenstate, so you have H with a non-degenerate eigenstate, so let's call it N like that. Then it follows from this theorem that this must be equal to 0. So there is no dipole, electric dipole. So this is a dipole operator. And the reason for this is because we just proved the theorem that if I have a non-degenerate eigenstate, then it must have a well-defined parity. Yes. So this has a well-defined parity. So you have the same parity, in other words. So then this matrix elements must be 0. Without doing any calculations, we can tell that it is 0. So we take, for example, the hydrogen S state, that's the lowest state, the ground state, then it has no dipole moment. It's spherically symmetric state. That's the next simple example. Okay, so that thing is we want to say about parity. So, yes. So maybe in the remaining few minutes we can start talking about time reversal symmetry. So time reversal symmetry is a little bit tricky when we talk about it in quantum mechanics because the corresponding operator turns out to be what is called anti-unitary. So unlike the usual operators in quantum mechanics that correspond to observables, this time reversal operator is anti-unitary. So we will go through that later, what we mean by anti-unitary operator. But let's just start by considering time reversal in classical mechanics. So as usual, we have Newton's equations. Force is equal to m times mass times acceleration. So obviously this equation is invariant under time reversal. So we change t to minus t because this is quadratic and it doesn't change the form of the equation. So x minus t is also a solution to Newton's equation. And if we look at Maxwell's equations, they are also invariant under this time reversal, provided, and this is important, so provided the magnetic field is reversed also. But if we regard the magnetic field as something from the outside, then this is not the case anymore. Yes. But if we think of the magnetic field as being generated by the system itself, so if we change t to minus t, then we also change the direction of the current. So then the magnetic field is also reversed. Then the Maxwell's equations are also invariant under time reversal. So time reversal, classical mechanics has a simple meaning. So we just change t to minus t. But in quantum mechanics, it's a bit more complicated. Okay, so maybe I can just continue a little bit here because we are at it. So the Schrödinger equation is not invariant under simple time reversal. So here means just changing t to minus t. And we can easily see this. So we start with a time-dependent Schrödinger equation. And if we change t to minus t, well, then dt becomes minus dt, and then we have minus t here, minus t here. So then this is not this is no longer a Schrödinger equation because I have a minus sign here. So So this is not a solution to the Schrödinger equation. It's quite different from the Newton's equations, where x of minus t is also a solution to the Newton's equation if xt is a solution. However, if we take the conjugate, so we take the conjugate here of this equation here, then we realize that it doesn't fulfill the Schrödinger equation. So this quantity here, the conjugate of the original wave functions, but with t becomes minus t, is a solution to the Schrödinger equation. And that is not in general the same as this original solution. It can be different because it's a complex conjugate. Okay, so that's kind of a difference between the time reversal in classical mechanics and in the quantum mechanics. So maybe we can have a break here and continue, let's say quarter past. Good. Unless you have questions. Okay, if not, then we just Okay, let's continue. Before I forget, when we were talking about this Heisenberg Hamiltonian, it just occurred to me during the break that you were talking about spin half systems. Yes, maybe some of you wondering why we have that particular ground state. So let me repeat quickly. So we have this Hamiltonian with minus j here, and we write it as Si set plus 1/2 j like that, and we say that this is a ground state here. So the reason is that these are spin halves. So then these two terms will kill the state, yes, because we have this S plus and S plus, and I is not equal to J. Yes. So this is I is not equal to J. We have nearest neighbor interaction. So then this is an eigenstate of SZ, of course. Okay, it's just a remarks, unless in case you are confused and wondering why this is the ground state of the Heisenberg Hamiltonian, talking about the spin half system. Okay, so going back to the time reversal, so we have seen that reversing the time does not keep the Schrödinger equation invariant. So we have to take complex conjugate. So it's a bit more complicated. So we want to introduce a time reversal operator in quantum mechanics. So actually the naming of time reversal is a little bit misleading because as we have seen that it's not just a matter of reversing the time. But before we do that, I would like to have a little digression to describe what it is anti-unitary operator. What is the definition of anti-unitary operator? So let's say that we call this operator like that, and we have some state alpha, state alpha, and we operate it with this anti-unitary operator. So it is a general thing. So I'm not talking about time reversal symmetry or anything like that. It's just a definition, general definition of anti-unitary operator. So I construct the state alpha tilde and beta tilde, which we define to be interacting on beta, like that. So by anti-unitary, we mean then that the overlap between alpha and beta states tilde is not equal to just beta, the overlap between the state beta and alpha, like what you have if you have a unitary operator, but rather is a complex conjugate. It's defined like that. So this is property number one, if you like. And then it has another property that if I operate this on some linear combination of states, doesn't have to be linear combination, but let's do this in a general way, like this. So C1 and C2 are complex numbers. Then this becomes C1 star, C1 alpha, that's C2 star and beta. So in other words, the anti-unitary operator affects complex number, unlike unitary operator, it doesn't care about complex number. So it turns the complex number into its conjugate, complex conjugate. So this is the definition of anti-unitary operator. And it doesn't matter whether we put the C1 here, here, here. It will change the complex number. So let's say let's do this explicitly. So if I write it like this, and then this also modifies the complex number C1 and C2, and we get the same result here. So it doesn't have to be directly in front of the operator. Okay, so this is the definition of anti-unitary operator. Now we want to define time reversal operator. So as we just said, the naming is a little bit unfortunate, but it is called time reversal operator. So it is defined in the following way. So we have position operator. We make time reversal. So we apply time reversal operator. So now theta is the time reversal operator. This is defined to be equal to x. So it does not alter the position operator. So that also implies that it commutes with the time reversal operator. However, with respect to momentum, time reversal reverse the momentum, versus the momentum from p to minus p. So it means that it anti-commutes with the time reversal operator. And these are the basic definition. It's the same thing here. It's basic definition of time reversal operator. So as you can see here, it may be more appropriate to call this operator theta as a momentum reversal operator rather than time reversal, because we don't have time here. At least it does not appear explicitly. Classically, of course, P is m dx dt. Then if we reverse the time, we will reverse the momentum too. But we don't have time in this definition here. Okay. Now, we want to show first that this time reversal operator is anti-unitary. And we require that this fundamental commutation relation between x and p equal to h bar is preserved. Is that correct? Preserve under time reversal. So we want to keep this fundamental commutation relations. So now if we look at time reversal transformation of this commutator. So then it is equal to minus xp from this properties, from this definition, because the x does not change sign, but the p changes sign. Yes, and then that's why we have minus here. And that is then equal to minus h bar, because we want to keep the this fundamental commutation. So this means that if we have IH bar here, that would imply that the time reversal operator changes the sign of the complex number. It's from I to minus I. So in general, if I have a complex number like this, it changes to C star. And so that's the basic properties of these time reversal operators. So you can see that that's also one of the definition of the, it's not one of the definition, but it's one part of the definition of anti-unitary operator. It converts the complex number into its conjugate. We also want to show that it fulfills the first condition. Yes, first condition. And this comes from the fact that we act time reversal operator on the position eigenstate, it remains position eigenstate up to phase factor. So we can see this, the fact that the x and the theta commutes. So if we look at the commutation relations between x and theta and apply it on some arbitrary ket vector x prime, then this becomes x theta x prime minus 2. So then well, I could have written this down immediately, but let's read step by step. So this becomes minus x prime. So x is a real number, so it's not affected by the complex conjugate. So this is 0 because this is 0. So then we can say that this state is also an eigenstate of the position operator. The same eigenvalue x prime. So then there is no degeneracy here. So it's one eigenvector. So then this must be proportional to x prime. Yes, and we choose the phase factor to be unity. So we have that property here. So let's now have a look at the effect of time reversal on a state alpha. So we want to show that this is equal to beta alpha star, like that. We want to show that it also fulfills the first condition for an anti-unitary operator. So we look at the state alpha tilde, and we introduce the completeness relation. Like that. So now we have to be careful here because we are operating on the whole thing here. So this is a complex number. So then it becomes integral x prime. we just show that this thing is equal to that one. But if we have a complex number inside, then that complex number turns into its complex conjugate. So then it becomes x prime alpha star. So we have to be careful here, yes, because this thing acts on the whole thing, not just on the state, this one state here. So then if we take the projection to the position eigenstate, that will then just give me alpha star x. Yes. So I might take projection to x on both sides. So then if we look at this overlap between two vectors of tilde and beta tilde, well, that's by definition is equal to x alpha tilde star x beta tilde x. Now we use this property here, so that becomes alpha x and beta star x, but that is equal to alpha beta star. So we just shown that the time reversal operator is an anti-unitary operator because it fulfills this property, yeah? And also that it converts complex number into its complex conjugate. Yes. So those are the basic properties we have shown that it is unitary. So now let's have a look at the consequence of this time reversal symmetry. So if we have a Hamiltonian, this is the general Hamiltonian here. Just do this in one dimension. No magnetic field, just a simple Hamiltonian. Take energy plus some potential. So this Hamiltonian is invariant under time reversal because we have p squared is quadratic. So this means that this invariant. So if it's invariant, it means that the operator commutes. Yes, h commute with h. So let's have a look at the effect of the time reversal operator on the Schrödinger equation. So we have time-dependent Schrödinger equation like this. That is equal to h at a. So now let's apply the time reversal operator on both sides. Like this. So again, this time reversal operator changes I to minus I. We can slide it through and we get theta thing on side t, like this. And then we use the property that it commutes with the Hamiltonian. So then this becomes h psi t. So by the way, we have defined this time reversal operator to always act to the right. Yes. So it's because we have an anti-unitary operator. So it is convenient to just define the operator to act on the right, to the right all the time. Yes. is if you have an you have a unitary operator, then of course it can act to the left and the right. This doesn't matter. But here we define the operator to act always to the right. So now we change t to minus t. Then we get h bar divided t is equal to h like that. So then we see that this state here, which we can call it to be the tilde state, is a solution to the time-dependent Schrodinger equation. So if psi t is a solution to the Schrodinger equation, then psi tilde defined to be is also a solution to the Schrodinger equation. So you can see that it's not just a matter of changing the time. Yes, we need to operate the state with a time reversal operator. So if we look at this more closely, maybe I have a picture actually. Let's see. And that's we have done. That's the here. That is just what I written down, I think. Okay, so this is what I want to show here. So let me use it. So if we consider this time reverse state tilde, so we denote the tilde as a time reverse state, defined to be this one here, we just found. This is also a solution to the time-dependent Schrodinger equations. And we want to have some kind of physical interpretation of this state. So we can write it in these two ways. So we have time development operator. Like that. So this is plus IHT divided by h bar. It's positive because we have minus t. So theta and h commutes. But we have to be careful when we do these commutations because the time reversal operator converts a complex number to its complex conjugate. Yeah. So this when we commute it here, we have to change the sign of the I. It's minus I instead. We have theta here, 0 like that. And so this is then these are just the time reverse state at 0. Now if we look at this two here, I think I can go back now to the slide here. So we have these two states. Hmm? So this is just obtained by commuting these two operators, the time reversal and this time development operator. So keeping in mind that it changes the complex number to its complex conjugate. So if we try to kind of interpret the meaning of this equation here, so try to draw a picture here on the left hand side. Um, so here we have a state at time t equals 0, so psi 0, so at time t equals to 0, and then we operate that state with this time development operator that corresponds to minus t. So that would be like rewinding the state. It's from 0 to minus t. So we go from this state here all the way back to minus t. Yes, we have a certain momentum in this direction. And then we perform time reversal, which in our definition, it reverses the momentum. So it reverses the momentum like that, at time minus t. So that's one way to look at the meaning of this equation here. And this one here should give me the same result. So here we start from state, same state, initial state, psi time t equal to 0. But instead of first rewinding the state to minus t, we reverse the momentum because we apply theta. So we reverse the momentum here from this direction to this direction. And then we evolve it. And we evolve it using our time evolution operator. So we evolve the time reverse state to time t. But here's because we reverse it, and it becomes minus t. So we end up with exactly the same state as it should be. So what we've been doing is a kind of opposite to what is done in the book. So the book, I think, starts from this equation here. So it starts from the assumption that these two processes are equivalent, and from there it works out the properties of the time reversal. But what we have done here is rather that we define time reversal operator as the one that reverses the momentum but keeps the position operator the same. And from this basic definition, we showed that indeed these two processes are equivalent. So I kind of prefer to do it that way because it becomes clear what is meant by time reversal operator. It means that you reverse the momentum. And as a consequence of this, we have this result here, that this process is the same as that one. So if we look at the time reverse wave function, so this is the projection onto the position eigenstate. Then the time reverse wave function is just given by this expression here. So I think we have worked this out before. So as we already said, that is not just reversing the time, but we must also take the complex conjugate of the wave function. So that's an important part of the time reversal operator. We can also look at the effect of the time reversal operator on angular momentum states. So to do this, we can make use of the properties of the spherical harmonics. So I have spherical harmonics like this. Then this is equal to minus 1 to the m times spherical harmonics with minus m. This comes from the properties of the spherical harmonics. So then, for integer j, we can then use this property here that the time reverse state, so this is the time reverse state here, so theta acting on the angular momentum state Jm. So that is the time reverse state of the angular momentum. It's just given by the star. Yes. So if I look at that here, so j equal to L here. So that is then just the complex conjugate. So then it implies that if I operate the time reversal on an angular momentum state Jm, then it will be multiplied by minus 1 to the m, and it goes to, and the state goes to j minus m, it's like what we have here. So then, if I apply the time reversal operator twice, you would then return the state to the original one. So if I apply this twice like this, then that becomes just Jm, because minus 1 to the power of 2m is 1, and minus m becomes m again. So then it implies that the square of the time reversal operator is equal to 1 for integer j. And we will consider a bit later the effect of time reversal on a spin-half system, which is a bit more complicated. So there is a kind of corresponding theorem associated with the time reversal operator, similar to the one we have for the inversion, is that if we have a Hamiltonian, which is invariant under time reversal, then we can show that the non-degenerate eigenfunctions must be real up to some multiplicative constant for spinless or integer spin systems. So how do we show this? So we have this theorem, and we have a Hamiltonian that commutes the time reversal. It's given, and we want to show that the eigen functions, so the eigenstates, well, not the eigenfunctions, because we're talking about the wave functions now. So if the eigenfunctions are non-degenerate, then they are real up to some multiplicative constant, provided we have this symmetry. So let's say that we have some eigenstate of the Hamiltonian. So this is equal to 10, like that. And we use this mutation relation so that it immediately gives us each thing on that one is equal to En. And so as we know this from the basic properties of symmetry, that this is also an eigenstate of the Hamiltonian with the same eigenvalue En. But now if we say that the eigenstate is a non-degenerate, it would imply that this state here must be just the same state, can only be the same state, and multiplied by some phase factor. Let's call it phi, call the phase phi. So then we have this is equal to like phi times like that. So now let's make a projection to the position eigenstate, because you want to look at the wave function. And that is equal to I phi x n, like that. So we know that this thing is just xn star. Yes, that's we had this before, that this thing is equal to psi star x minus t. Yes, with t there's no t, so we can put t equal to 0. So then it's just a complex conjugate. Yes. So that is equal to the right hand side. So we can multiply then both sides by minus I, 5.2. So that's equal to 5.2 xn. So that's the proof, yes. So the left-hand side is just the complex conjugate of the right-hand side, or vice versa. So then it's real. So this quantity here, or this one here, is real. So that means that the eigenfunction is real up to multiplicative factor, phase factor. So that's the proof. So in the remaining 5 minutes, I want to can start talking about the time reversal for spin-half systems. And this is more tricky. So far we have been talking about time reversal for spinless systems and spin-one system. Now we have time reversal for spin-half systems. So how do we do this? So we want to ask the questions of going to ask the following question. So we have, let's say, spin up state. What do we get here? So we use the property that the time reversal operator anti-commutes. So with the angular momentum operator, it reverses the angular momentum. So it is kind of clear also, because angular momentum is position operator times the momentum operator, and the time reversal operator reverses the momentum, but keep the position operator same. Then we get this property here. So now if we look at this state here, we can then use this property. So that implies that in J, the anti-commute. So now we apply SZ in this state, then it's equal to minus SZ because of this anti-commutivity. Then we see that this is equal to minus h bar upon 2, like this. So then we see that this state here is an eigenstate of Sz, but with eigenvalue minus h bar upon 2. So that implies that this state must be proportional to the spin down state. Yes, multiplied by some phase factor. So and eta here is the phase factor. So this is the first result. So we also want to know the effect of the time reversal on the spin down state. And to do that, we observe that this rotation operator around y-axis by pi, so we operate it on that state, that gives me spin down, and we operate this rotation operator by pi on the spin down state, that will turn it into spin up, but with a minus sign. So you can easily check this using the explicit form of the rotation operator for the spin half. So this also follows from the fact that this thing is just e to the minus h bar is I times 2 pi on the spin up. And that gives me minus spin up. So here we recall that we rotate the spin state by 2 pi. The state acquires a minus sign. So then, using this result here, we can figure out the effect of theta on the spin down. So we convert this first to spin up states. We have, so we run spin down states in terms of the rotation of the spin up state by pi, like so. And then I can insert unit operator. Like that. So this thing here, so we make use of the fact that the angular momentum commutes. Anti-commutes with theta, but at the same time it converts I into minus I. Yes, so then this becomes just the same thing. Like so. So now we know that this thing is just eta that spin down like this. And that rotation operator acting on the spin down state turns it into spin up. So that becomes then, but with the minus sign, so then we get eta spin up like this. So it turns the spin up, spin down state into a spin up state, but with a minus sign. Yes, this is what we get. And from the previous result, we have eta down. This just differs by a sign here. Okay, I'm going over time, so this could be a good place to stop. We still have a little bit to go through. That take quite some time. Thanks. I will stop here. So, are there any questions about this time reversal? If there are no questions, then we meet again, I think, next week on Tuesday. Yes.
Can I ask a question?
Yes.
So if or when you get more information about the exam, are you going to post that on the Canvas
On the
page?
Canvas, yes. I will.
Yeah.
Thanks for reminding me. Yes.
Okay.
I thought about that also. Yes. Yeah.
Thank you. Have a nice day.
Okay. Thank you. Bye bye.
Thanks. Bye.
Bye bye.